A jet engine is a type of reaction engine, discharging a fast-moving jet of heated gas, usually air, that generates thrust by jet propulsion. While this broad definition may include rocket, water jet, and hybrid propulsion, the term jet engine typically refers to an internal combustion air-breathing jet engine such as a turbojet, turbofan, ramjet, pulse jet, or scramjet. In general, jet engines are internal combustion engines. Air-breathing jet engines typically feature a rotating air compressor powered by a turbine, with the leftover power providing thrust through the propelling nozzle. This process is known as the Brayton thermodynamic cycle. Jet aircraft use such engines for long-distance travel. Early jet aircraft used turbojet engines that were relatively inefficient for subsonic flight. Most modern subsonic jet aircraft use more complex high-bypass turbofan engines. They give higher speed and greater fuel efficiency than piston and propeller aero engines over long distances. A few air-breathing engines made for high-speed applications, ramjets and scramjets, use the ram effect of the vehicle's speed instead of a mechanical compressor. The thrust of a typical jetliner engine went from 5,000 lbf, 22 knots, de Havilland Ghost turbojet, in the 1950s to 115,000 lbf, 510 knots, General Electric G90 turbofan, in the 1990s, and their reliability went from 40 in-flight shutdowns per 100,000 engine flight hours to less than 1 per 100,000 in the late 1990s. This, combined with greatly decreased fuel consumption, permitted routine transatlantic flight by twin-engined airliners by the turn of the century, where previously a similar journey would have required multiple fuel stops. The principle of the jet engine is not new. However, the technical advances necessary to make the idea work did not come to fruition until the 20th century. A rudimentary demonstration of jet power dates back to the Aeolipile, a device described by Hero of Alexandria in 1st century Egypt. This device directed steam power through two nozzles to cause a sphere to spin rapidly on its axis. It was seen as a curiosity. Meanwhile, practical applications of the turbine can be seen in the water wheel and the windmill. Citation needed. Historians have further traced the theoretical origin of the principles of jet engines to traditional Chinese firework and rocket propulsion systems. Such devices used for flight is documented in the story of Ottoman soldier Lagari Hassan Chalebi, who reportedly achieved flight using a cone-shaped rocket in 1633. The earliest attempts at air-breathing jet engines were hybrid designs in which an external power source first compressed air, which was then mixed with fuel and burned for jet thrust. The Italian Caproni Campini N1 and the Japanese Zu-11 engine intended to power Oka kamikaze planes towards the end of World War II were unsuccessful. Citation needed. Even before the start of World War II, engineers were beginning to realize that engines driving propellers were approaching limits due to issues related to propeller efficiency, which declined as blade tips approached the speed of sound. If aircraft performance were to increase beyond such a barrier, a different propulsion mechanism was necessary. This was the motivation behind the development of the gas turbine engine, the most common form of jet engine. The key to a practical jet engine was the gas turbine, extracting power from the engine itself to drive the compressor. The gas turbine was not a new idea. The patent for a stationary turbine was granted to John Barber in England in 1791. The first gas turbine to successfully run self-sustaining was built in 1903 by Norwegian engineer Egidius Elling. Such engines did not reach manufacture due to issues of safety, reliability, weight and, especially, sustained operation. The first patent for using a gas turbine to power an aircraft was filed in 1921 by Maxime Guillaume. His engine was an axial flow turbojet, but was never constructed, as it would have required considerable advances over the state-of-the-art in compressors. Alan Arnold Griffith published an aerodynamic theory of turbine design in 1926, leading to experimental work at the RAE. In 1928, RAF College Cranwell cadet Frank Whittle formally submitted his ideas for a turbojet to his superiors. In October 1929, he developed his ideas further. On the 16th of January, 1930, in England, Whittle submitted his first patent, granted in 1932. The patent showed a two-stage axial compressor feeding a single-sided centrifugal compressor. Practical axial compressors were made possible by ideas from A. A. Griffith in a seminal paper in 1926, An Aerodynamic Theory of Turbine Design. Whittle would later concentrate on the simpler centrifugal compressor only. Whittle was unable to interest the government in his invention, and development continued at a slow pace. In Spain, pilot and engineer Virgilio Lerre Ruiz was granted a patent for a jet engine design in March 1935. Republican President Manuel Azaña arranged for initial construction at the Hispano-Suiza aircraft factory in Madrid in 1936. But Lerre was executed months later by Francoist Moroccan troops after unsuccessfully defending his seaplane base on the first days of the Spanish Civil War. His plans, hidden from Franceursts, were secretly given to the British Embassy in Madrid a few years later by his wife, Carlotta O'Neill, upon her release from prison. In 1935, Hans von Ohain started work on a similar design to Whittle's in Germany, both compressor and turbine being radial, on opposite sides of the same disc. Initially unaware of Whittle's work, von Ohain's first device was strictly experimental and could run only under external power, but he was able to demonstrate the basic concept. Ohain was then introduced to Ernst Heinkel, one of the larger aircraft industrialists of the day, who immediately saw the promise of the design. Heinkel had recently purchased the Herth Engine Company, and Ohain and his master machinist Max Hahn were set up there as a new division of the Herth Company. They had their first Hes 1 centrifugal engine running by September 1937. Unlike Whittle's design, Ohain used hydrogen as fuel, supplied under external pressure. Their subsequent designs culminated in the gasoline-fueled Hes 3 of 5 knots, 1,100 lbf, which was fitted to Heinkel's simple and compact He 178 airframe and flown by Erich Warsitz in the early morning of August 27, 1939, from Rostock Marina He Aerodrome. An impressively short time for development. The He 178 was the world's first jet plane. Heinkel applied for a U.S. patent covering the aircraft power plant by Hans Joachim Pabst von Ohain on May 31, 1939, patent number US 2256198, with M. Hahn referenced as inventor. Von Ohain's design, an axial flow engine, as opposed to Whittle's centrifugal flow engine. Austrian Anselm Franz of Junkers Engine Division, Junkers Motoren or JUMO, introduced the axial flow compressor in their jet engine. JUMO was assigned the next engine number in the RLM 109-0XX numbering sequence for gas turbine aircraft power plants, 004, and the result was the JUMO 004 engine. After many lesser technical difficulties were solved, mass production of this engine started in 1944 as a power plant for the world's first jet fighter aircraft, the Messerschmitt Me 262, and later the world's first jet bomber aircraft, the Arado R-234. A variety of reasons conspired to delay the engine's availability, causing the fighter to arrive too late to improve Germany's position in World War II. However, this was the first jet engine to be used in service. Meanwhile, in Britain the Gloucester E-2839 had its maiden flight on the 15th of May, 1941, and the Gloucester Meteor finally entered service with the RAF in July 1944. These were powered by turbojet engines from Power Jets Limited, set up by Frank Whittle. The first two operational turbojet aircraft, the Messerschmitt Me 262 and then the Gloucester Meteor, entered service within 3 months of each other in 1944. The Me 262 in April and the Gloucester Meteor in July. The Meteor only saw around 15 aircraft enter World War II action, while up to 1,400 Me 262 were produced, with 300 entering combat, delivering the first ground attacks and air combat victories of jet planes. Following the end of the war, the German jet aircraft and jet engines were extensively studied by the victorious Allies and contributed to work on early Soviet and US jet fighters. The legacy of the axial flow engine is seen in the fact that practically all jet engines on fixed-wing aircraft have had some inspiration from this design. By the 1950s, the jet engine was almost universal in combat aircraft, with the exception of cargo, liaison, and other specialty types. By this point, some of the British designs were already cleared for civilian use, and had appeared on early models like the de Havilland Comet and Avro Canada jetliner. By the 1960s, all large civilian aircraft were also jet-powered. leaving the piston engine in low-cost niche roles such as cargo flights. The efficiency of turbojet engines was still rather worse than piston engines. But by the 1970s, with the advent of high-bypass turbofan jet engines, an innovation not foreseen by the early commentators such as Edgar Buckingham, at high speeds and high altitudes that seemed absurd to them, fuel efficiency was about the same as the best piston and propeller engines. Jet engines power jet aircraft, cruise missiles, and unmanned aerial vehicles. In the form of rocket engines, they power model rocketry, spaceflight, and military missiles. Jet engines have propelled high-speed cars, particularly drag racers, with the all-time record held by a rocket car. A turbofan-powered car, Thrust SSC, currently holds the land speed record. Jet engine designs are frequently modified for non-aircraft applications, as industrial gas turbines or marine power plants. These are used in electrical power generation, for powering water, natural gas, or oil pumps, and providing propulsion for ships and locomotives. Industrial gas turbines can create up to 50,000 shaft horsepower. Many of these engines are derived from older military turbojets such as the Pratt & Whitney J57 and J75 models. There is also a derivative of the P&W JT8D low-bypass turbofan that creates up to 35,000 horsepower, HP. Jet engines are also sometimes developed into, or share certain components such as engine cores, with turboshaft and turboprop engines, which are forms of gas turbine engines that are typically used to power helicopters and some propeller-driven aircraft. A turbojet engine is a gas turbine engine that works by compressing air with an inlet and a compressor, axial, centrifugal, or both, mixing fuel with the compressed air, burning the mixture in the combustor, and then passing the hot, high-pressure air through a turbine and a nozzle. The compressor is powered by the turbine, which extracts energy from the expanding gas passing through it. The engine converts internal energy in the fuel to increased momentum of the gas flowing through the engine, producing thrust. All the air entering the compressor is passed through the combustor and turbine, unlike the turbofan engine described below. Turbofans differ from turbojets in that they have an additional fan at the front of the engine, which accelerates air in a duct bypassing the core gas turbine engine. Turbofans are the dominant engine type for medium and long-range airliners. Turbofans are usually more efficient than turbojets at subsonic speeds, but at high speeds their large frontal area generates more drag. Therefore, in supersonic flight, and in military and other aircraft where other considerations have a higher priority than fuel efficiency, fans tend to be smaller or absent. Because of these distinctions, turbofan engine designs are often categorized as low bypass or high bypass, depending upon the amount of air which bypasses the core of the engine. Low bypass turbofans have a bypass ratio of around 2:1 or less. A propfan engine is a type of air-breathing jet engine which combines aspects of turboprop and turbofan. Its design consists of a central gas turbine which drives open-air contra-rotating propellers. Unlike turboprop engines, in which the propeller and the engine are considered two separate products, the propfan's gas generator and its unshrouded propeller module are heavily integrated and are considered to be a single product. Additionally, the propfan's short, heavily twisted variable pitch blades closely remember the ducted fan blades of turbofan engines. Propfans are designed to offer the speed and performance of turbofan engines with fuel efficiency of turboprops. However, due to low fuel costs and high cabin noise, early propfan projects were abandoned. Very few aircraft have flown with propfans, with the Antonov An-70 being the first and only aircraft to fly while being powered solely by propfan engines. The term advanced technology engine refers to the modern generation of jet engines. The principle is that a turbine engine will function more efficiently if the various sets of turbines can revolve at their individual optimum speeds, instead of at the same speed. The true advanced technology engine has a triple spool, meaning that instead of having a single drive shaft, there are three, in order that the three sets of blades may revolve at different speeds. An interim state is a twin-spool engine, allowing only two different speeds for the turbines. Ram compression jet engines are air-breathing engines similar to gas turbine engines insofar as they both use the Brayton cycle. Gas turbine and ram compression engines differ, however, in how they compress the incoming airflow. Whereas gas turbine engines use axial or centrifugal compressors to compress incoming air, ram engines rely only on air compressed in the inlet or diffuser. A ram engine thus requires a substantial initial forward airspeed before it can function. Ramjets are considered the simplest type of air-breathing jet engine because they have no moving parts in the engine proper, only in the accessories. Scramjets differ mainly in the fact that the air does not slow to subsonic speeds. Rather, they use supersonic combustion. They are efficient at even higher speed. Very few have been built or flown. In a jet engine, each major rotating section usually has a separate gauge devoted to monitoring its speed of rotation. Depending on the make and model, a jet engine may have an N1 gauge that monitors the low-pressure compressor section and/or fan speed in turbofan engines. The gas generator section may be monitored by an N2 gauge, while triple spool engines may have an N3 gauge as well. Each engine section rotates at many thousands RPM. Their gauges therefore are calibrated in % of a nominal speed rather than actual RPM, for ease of display and interpretation.